All right, in this recording, we will go over task 2 of recitation 6, building an ALU. So to recap, an ALU is an arithmetic logic unit. It's a circuit that takes two inputs and produces an output. The output is based on a certain operations. For example, the ALU can add, subtract, or not the inputs. And you have a selector down here to choose from amongst the possible operations that the ALU will output. For instance, if you had an operation like add reg1, reg2, reg3, which would be adding register 2 and register 3 and putting the result in register 1, our input could be the values of register 2 and 3, and our result could be written into register 1. Now let's take a look at what type of ALU we will be building for this recitation. So for ALU, we take in, of course, an input data 1, input data 2, and output and output data. There's an op type that selects which operation that we want to do, and the operations are add, subtract, or, and not. Now note that in this recitation, we can use components that are already built in Logisim, so the adder and the subtractor, for instance. But for homework 4, you actually have to implement those yourself, which shouldn't be too difficult since you already started working on that for homework 3. All right, now let's head over to Logisim to start to implement the circuit. So we need, first of all, we need the input and output pins. For the input pins, remember that we have input data 1, and similarly input data 2. We have an op type, and those are our 3 input pins as specified in the recitation document. So let's think about how big we need to make our inputs. For our input data, we'll be taking values from registers, right, and performing operations on them. So they should each be the size of a register, which is 16 bits in this case. So we can go and set their data bits to 16. For the op type, we're going to be choosing between 4 different operations, and we only need 2 bits to select that. So for data bits, we can choose 2. All right, next remember that we need an output pin, of course, and we can name that output data. And of course, this should be the size of a register as well, so we will set that to 16 bits. Now the output is linked to the ALU, if you remember the diagram that we just saw. And the ALU is simply a mux. So if we take a mux, we can connect it to the output data, and then we can set the number of bits. So it should have 2 select bits since the op type is the op type selector is 2 bits, and it should be able to take in 16 bits. Perfect. Now we can just go along and implement each of the operations. So for add, we can just drag out an adder. The input 1, well, actually, we should probably use some tunnels. So in this case, we can change, or we can add some tunnels and make sure to set their respective data bits as well. And for the op type as well. Okay, so the ALU op, or the op type, should be going to select which operation to do. So this should be going to the select port of the mux. And each port here will indicate which operation to do. So if we go back to the recitation document, we see that 0, 0 is add. So we can drag in an adder and then have the results of the adder go into 0, 0. Now we need to make our adder 16 bits. Of course, as said earlier, for this recitation, we can use components already built in Logisim, but for your homework, you would have to implement your own adder and subtractor. And the inputs will just be the input data. All right, and in this case, we're not worrying about the overflow, but in your homework, you could build something that can detect overflow as well. All right, next, 0, 1 will be subtract. So the next input into the mux will be a subtraction unit. Of course, the inputs are analogous. And make sure that it's the correct size. All right. Next, we need to implement OR and NOT. OR is 1, 0 and NOT is 1, 1, so the third and the fourth. For OR, we can just drag out an OR gate. And similarly, OR the two inputs. All right. And lastly, we're going to implement NOT. So of course you can't NOT two values together. That doesn't really make any sense. So in this case, we'll just be NOTing the first value, right? In your CPU, if you have a NOT instruction, you wouldn't have two registers. You would just have one register there. So let's simply drag out a NOT gate and use in1 to NOT. All right, perfect. We now have a fully functioning ALU as specified by the recitation document, and we can test it a little bit. So using the poke tool, we can, for example, test the different operations. For 0, 0, remember that that's add. So if we add, for example, 1 and 1, we should expect an output of 2, or 1, 0, which is what we see here. For subtract, we should probably see 0 for subtracting 1 from 1. And that is indeed what we see in the output. For ORing, let's say we do two different bits to OR. So maybe the first bit of, or the 0th bit of in1 and the first bit of in2. And if we do ORing, we see that both of these bits light up as expected. And then for NOTing, we'll simply be NOTing the input 1. So it should just be all 1s except the 0th bit is a 0. And we see that as expected. Now for your homework, it would be wise to test some more corner cases for ALU, just to test out if each of your components are working in terms of your adder, subtractor, and other things. But in this case, we can do a simpler checking to make sure that our circuit functions as expected. All right, if we go back to the diagram from lecture, we see that you can optionally put some extra information in your ALU. For example, if the result is 0, or if there was an overflow detected in one of the operations. Feel free to implement this in your homework, but this will not be part of recitation.